we don't have quite the same time scales or the same power scale. This is excess power here, this is time scales here. But you can see we both show a band here and we both show a band here. And in fact, quite a few of the points, if you line them up, like right through there, those points go up and down in fairly consistent manner in that period. Or since the time scales are different, I can shift this over. That earlier period, there's a large peak that goes up and comes down, and there's a band right in here. So you can see that the two methods are giving pretty good agreement. The main difference is that the Fleischmann method, which I'm sure is more accurate, much more detailed in determining the heat transfer coefficient, shows higher excess power than what I recorded. This is in excess enthalpy, but that would be equal to 0.347 watts right there. So you're in excess of 300 milliwatts, or 0.3 watts over in this region right here. But it's remarkable that two different methods, the one I worked out in Japan and what Martin Fleischmann did, we show exactly the same features. The basic features are both present. Now, if you look at what Japan reported, what their data shows, they come up with a much smaller radiative heat transfer coefficient because they use that first heating cycle where there is positive feedback, therefore large errors. Therefore, they came up with a much smaller constant, and they use a much larger value here. They do show some bands here, but look where they put 0. They put 0 right through here, so they say Fleischmann-Pons calorimetry is very inaccurate. You have large fluctuations. What they should say is there's excess heat fluctuations and their calibration is off. That would be more accurate. but they do show some of the same features, but they just have calibrated it incorrectly. So what, 5 minutes? Right. Okay, I'll just try to hurry on through this then. This is the palladium cerium. It also shows excess power, reaching high as maybe 200 milliwatts through here. And again, the NHE method in Japan, they say there was no excess heat in this experiment. And in fact, the Japanese report, despite my writing this up and before I left Japan and showing these results to them, the Japanese report boils it down to one paragraph and says that I had no excess heat, which I don't understand. But I think there's always a problem when you try to transfer a calorimetry to another laboratory. If the other laboratory doesn't understand it, doesn't do it right, they're not going to get the correct results. So Fleischmann, when he tried to transfer his calorimetry to NHE in Japan, they changed things, they used their own method of data analysis, they got things incorrect, and they claimed there's no excess heat, and they reported there's errors in the calorimetry. I had the same problem when I tried to transfer China Lake calorimetry to NRL. Even though I tried to show them exactly what I was doing when I got back to Naval Research Laboratory, they wanted a larger sail so they could do loading studies, so they scaled it up. They added 4 extra lead wires. Even though we told them about data averaging, they did not average the cell voltage and temperature like they should have. And they had a very poor room where the temperature's out of control. And therefore, when they wrote their final report, they reported an error of plus or minus 200 milliwatts in their calorimetry. Well, mine only had an error of plus or minus 20 milliwatts. And for a year or two, I thought they were improving things. And towards the end of the program, I found they increased the error by a factor of 10. And since I've never seen anything larger than 500 milliwatts, they would not see anything either with that kind of error. So I had a similar experience trying to transfer calorimetry to a different laboratory. Summary, the Fleischmann-Pons calorimetry, you have to get an accurate determination of the radiative heat transfer coefficient and the water equivalent of the cell, or you should not even try to use it if you're not going to try very hard to get those things right. The alternative NHE method, which was published in the Monte Carlo meeting, is a complete failure. I would cross that article out for me if you go back to that publication. The heat transfer coefficient is determined incorrectly, as well as the water equivalent of the cell. And therefore, the NHE method confuses excess power with the error of the Fleischmann-Pons calorimetry. In this study, palladium boron and palladium cerium showed significant excess power in the Fleischmann-Pons cell, even though the NHE report does not acknowledge that in Japan. Just a note, I hate being critical of Dr. Sami and people at NHE. They were very good friends, but scientifically they did things wrong. So I have no choice to take this stand. But I did very much enjoy working with the people in Japan while I was there. And just acknowledgement, NEDO, New Energy Development Organization, I'd like to express appreciation to them for this 5-month period I had in Japan. And the people I worked with at New Hydrogen Energy Laboratory, Dr. Sami, and Sumi, and Marie Husado. And also I'd like to thank my wife who did a lot of help on her computer and typing to make all this possible. Okay, thank you.
Now we have time to discuss.
As a simple question, how do you compare the data of palladium cerium and palladium boron? Which gives more excess power?
In this experiment, the palladium boron gave maybe 100 milliwatts more. The palladium cerium was about 200 milliwatts, and the palladium boron is maybe 350 to 400 milliwatts in this case.
What's the current you're using, and what was the temperature? You mentioned that.
The current, typically the current was between 400 to 600 milliamps. And what was the other question?
The temperature?
The temperature, typically 50 to 60, in the range of the 50s or 60s degrees Celsius. Except we later drove this cell to boiling, and maybe Martin will talk about that tomorrow. The excess helium got larger during the boil-off period.
Did you start by loading at low current, or did you go directly to the high current?
I started off by loading at 150 milliamps for 3 days.
But you don't show that?
No, I didn't show that here.
Okay.
Well, it was a very early, the first heating cycle was at the low current, 150 milliamps. The Japan used for that calibration. So that calibration, that first calibration was low current, 150 milliamps. That's another possible problem. They calibrated at a much lower temperature than where we normally ran. They calibrated that first heating cycle where it was still low current, still doing 150 milliamps. The cell temperature is probably only about 30 degrees during that first calibration that they used.
Could you comment on Ed Storm's work yesterday with respect to using heating as a technique, using a heater as a technique for calibration as opposed to using the electrolytic power, which he had 2 curves in his yesterday. I'm a little curious about how you would judge Ed's result and comments and the whole process that you and Martin used.
Martin, do you want to answer that?
I just want to say, I'll say something about that tomorrow. But Ed is wrong. If the cell is adequately stirred, then of course you can use the heater power. But you must apply the heater power while the cathode process is going on. You must have the same rate of stirring, otherwise of course you might have any thing.
I think I would agree. I've used both, actually. I've calibrated by increasing the current of the cell and use that as a calibration, and that seems to give a fairly good result. But I think the heating pulse is maybe more accurate in the end.
Can you say something about the relative accuracy of the calibration methods?
In my opinion, using this heater in the cell is more accurate, in my opinion, than just increasing the current and using that as a calibration. And for any of these, you have to assume that the excess heat is not changing. Either it's absent or it's not changing, or else that's going to throw it off anyway.
I have a comment about that. Yeah, he's doing electrochemistry as well as heating. You know, that's why it's correct.
Right.
Ed was doing separately.
Oh, okay.
That's the explanation.
Oh, okay. If you're not doing any electrochemistry, then the heater is probably not too accurate. And I tried this at China Lake too. You have to devise some method for stirring. If you're just going to use a heater, and no electrolysis. There's no gas bubbles to stir, so you have to devise something else to stir it. Otherwise, it'll be very inaccurate.
One more? All right.
Mallove, has NHE ever responded to these criticisms?
This happened several months ago, and you know, I was periodically corresponding to Dr. Sami and Mr. Matsui by email, and when this happened with Jed Rothwell and so on, I wrote a letter, a real nice letter to him, just explaining that I had to stick by what I thought was correct scientifically, but I told him I very much enjoyed working with him in Japan, and I've never heard from him since. So.
Okay, thank you very much again.
Only 30 minutes. You know about the show.
We will move to the next speaker.
Experiments with Harwell cells, which we simply
The next speaker is Professor Kim from Purdue University. He will talk about the ultra-low energy nuclear fusion for both nuclear compliance in ion channels.
Is really a multi-compartment cell. The result of this is,
This is our outline on my talk. What I'm going to tell you.
Water over the dam, literally.
What I'm going to tell you is new since last conference, and completely different than existing theories, including mine. All of the mathematical detail, the derivation,
Microphone.
all of the mathematical derivation is published. So I won't go into detail the derivations of the theory. I'll just outline how we do. The motivation of doing this so-called coherent quantum state nuclear fusion, which is more or less aim of the preparator or other theorists in this room, came from work on Bose-Einstein condensation, which was a completely different subject. We developed a theoretical method to do that part, and then realized that we can apply this to coherent quantum state nuclear fusion. But before I get into that new approach, let me remind you what the problem is with the conventional theory. The several speakers has mentioned the gamma factor, and actually it's very simple derivation in undergraduate quantum mechanics book, and you get this factor here. But I'd like to remind you that this is not the fundamental derivation, it's the WKB approximation. I think one should really realize that this is not the first principle derivation, which many of my colleagues in nuclear physics forget. What we like to look at is essentially those three reactions. I'll discuss these two reactions, and then finally this transition without no gamma rays. Now, if you take gamma factor, you get this kind of number. Look at this number. I don't think this makes a physical sense. Even if the electron scatter is extremely small. And of course, Kasagi is claiming you have to put the electron screening energy of this order to explain its data. And the original freshman cones, if you extract from their data, is 10 to the minus 20, and Steve Jones' claim will correspond to about 10 or 12 order of magnitude lower. So this is a benchmark figure we'll work with. Now, in terms of rate, that's very nice. Again, you can have a benchmark work. Notice this number I'm going to use later on. Freshman cones is about this rate for deuterium, and Steve Jones will be at this point. And it's nowhere near this number. Okay, now that is sort of background. Does the gamma factor derivation can we improve that? And we did look at from a quantum mechanical point of view, and derived a formula based upon quantum scattering theory, which I regard to be more rigorous. And in fact, one can use optical theorem, which is very rigorous result, to turn around and get the new formula. And when we did that, we came up with modification of gamma factor. And instead of ordinary form we had before, this is the extra factor you obtain by doing quantum scattering calculation using optical theorem. So there are large uncertainty in gamma factor. Now, I won't go into more than that because I like to dwell on different theory. And this was originally last conference. We speculated that possibly Bose-Einstein condensation mechanism might help us to explain many of the details. But we realized that we are just borrowing Bose-Einstein condensation for the atoms, which is neutral bosons, while the deuteriums or charged particles, so the same formulation should not be applicable. So we had to reformulate the theory to come up with description. Now, what we are trying to do is trying to solve this many-body Schrödinger equation. It's easy to write and very rigorous, but in order to get the solution, it's not that easy. So, but before I do that, try to discuss approximate solution. Let me retest this same many-body Schrödinger equation in terms of creation annihilation operator. And the reason I like to mention this is that Dirac, in 1933 quantum mechanics book, in one of the chapters, made this statement that for large n bosons, this commutator, instead of this coordinate delta, can be set to 0 because operator, expectation value operator are so large. And physical consequence of that, he states that is impacting bosons behave like an independent particle, although there is an interaction between them, that interaction becomes sort of background potential. So the interaction between pairs washed out. Now that is a very interesting, important conjecture. No one has proven it, but we'll see our results are consistent with his conjecture. Now, conventional Bose-Einstein condensation is mostly used this so-called Ginzburg-Gross-Pitevsky equation, and this is a nonlinear Schrödinger equation you derive. But in order to derive this, your interaction has to be contact interaction, not the repulsive Coulomb type. So now I'm going to describe how we solve this problem. We invented the method of so-called equivalent linear two-body method for charge boson. And what it is that you're trying to obtain your many-body wave function, but that's very difficult exactly. So what we do is we'll approximate this with some sort of trial wave function in which those three parameters are like the x, y, z coordinate. So instead of 3 times n degree of freedom goes to 3 degree of freedom, which we can solve. And by putting this in variational principle, one can generate an equation which is two-body equation, and that we know how to solve. We have tested this with a number of different exactly known solutions, like a one-dimensional case, and found that this method is very accurate for very large n. And later you see we are talking about million particles in a trap. So this may be a reasonable approximation. So to do the charged particle many-body problem, we start with this many-body Hamiltonian. And notice that I am including Coulomb interaction from a beginning. That is, all the pairwise Coulomb interaction is explicitly included. They are in harmonic oscillator confining potential, and trying to get the exact solution of this Hamiltonian. And we use this ELTV method, and then come up with this two-body equations. And everyone knows how to solve two-body Schrödinger equation. This is almost looking like a Schrödinger equation in this coordinate row, which is defined here. This looks like centrifugal term, and very similar. And the potential, effective potential, becomes something like that. Now remember, this equation came out of the original Hamiltonian, which includes all pairwise Coulomb interactions. Now we can solve this equation, and I won't go into the detail. For large n, we can get sometimes the exact solution, but I'll skip that part of derivation because most of you may not be interested in the mathematical. But let me see, once we solve that equation, we have a wave function, eigenvalue, and eigenfunctions, and that function is many-body wave function. Now, in order to calculate a nuclear fusion process, one has to have transition operator, which is a nuclear potential. That is, initial many-body state will two pair in the many-body state will interact through the nuclear interaction, and then make a transition to final state. So now we have to introduce short-range nuclear interaction operator to really calculate transition probabilities. And we go back to our optical theorem formulation, in which we show that scattering amplitude can be related to a cross-section in this way, and so that whatever form of the short-range nuclear interaction you assume, one can make a connection to real nuclear scattering parameters. And we can relate our interaction coupling strength with the known experimental number. This is the S factor you extract from the low energy data. Remember, this S factor is nearly constant, whereas the gamma factor is the one which changes so much. So the whatever potential you assume, this is called the Fermi potential, essentially contact interaction, delta function interaction. But whatever interaction you assume, you have to determine what is the coupling constant, appropriate coupling constant, and that's given by A, and A is related to known experimental number. So we can essentially use the experimental number to describe this transition operator. So that's taken care of. Fusion rate can be computed as a transition rate using the transition operator. Remember, this is a pairwise interaction, so I have to do all of the deuterium pair in the system. And if we use our solution, the wave functions, approximate wave function, then it will become this form. And this can be computed using our solution. And let me now go into asynchronous trap. Deuteriums of both nuclei confined in a single trap. That rate, after we do the calculation, becomes something like that. Now, omega squared, remember, is a harmonic oscillator parameter, but that can be related to size of harmonic oscillator. So we get the one prediction formula, which look like this. If you now, instead of parameter omega squared, if you relate that to the average size of the oscillator, by using our ground state expectation value, you can calculate that. So this parameter is essentially translated into size of the confining potential. And if we put all that, we get that. Now, remember, B is non-constant coming from nuclear interaction. Omega is the one we cannot calculate. That is the probability of ground state. And in neutral Bose-Einstein condensation, J achieved this omega to be nearly 1 by going to a non-Kelvin temperature, because as you cool, all of the bosons go to ground state. But this is charged bosons, and not necessarily you can pack all of the particle in a ground state even if you lower the temperature. So we don't know how to calculate this. This is only one parameter in the theory. Now, with this formula, we like to suggest experiment using Henning trap. That is, recently these people achieved the ion plasma confined. This case was a beryllium-9, and they get the density 4 times 10 to the 8 per cubic centimeter. And the number they confined is like 1 million particles in this small space. So this is the ideal test of our formula. If one can put a deuterium pair and maybe increase the number of deuterium confined there. So we are proposing mostly to high energy physicists who have been using this type of penny trap to do the anti-proton studies. They do confine anti-proton, which comes out of accelerator, and then using this type of penny trap, they confine them. So what our suggestion is to inject the plus and see whether we can observe some of the predictions. But more interesting thing is to apply this to cold fusion. If I make a multiple trap, you just simply multiply number of traps in the system, and then you can rewrite that. And it turns out that this expression goes like density, deuterium density squared. So obviously, the high loading is essential to maximize this expression, which is consistent with most of the observation reported at this conference. So in order to apply this, I am going to assume, I am going to look at the Arata Zhang's data, and he had something like 25 nanometer, but let's assume 40 nanometer particle, powder particle. And let's assume this is a transient situation where deuterium can go in and out, but it's saturated to the same density as the paradigm errors, named this number is present here. Then with this volume, you are having about 1 million deuterium compound at a given time. And now, if you have that kind of situation, if this process happens, you do not need gamma ray to conserve momentum, because the entire this coherent quantum state act like one quantum object. They can absorb the recoil momentum. So let me use this model for the Arata's experiment and see what kind of number we can end up with. Before I do that, let me spell out number for their experiment, Arata Zhang. They eat 3 grams, so it's got this much paradigm in the entire system, and so on, and the number of deuterium is same as that, and so on. So once I take all these experimental numbers, I can translate and put into my formula. And I told you there's one parameter which we cannot determine. Hopefully, experiment will tell us what that would be. For this type of radiation reaction, with the Q value known, you end up with single trap rate is that, but with a multiple trap, you get this large number, which means omega can be very small, which is reasonable, because the occupation number for the ground state, if you have 1 million particles in the box, you may have more than 1 million states, or maybe 3 order of magnitude more states, and if you distribute particles equally to all states, then you would see that omega could be very small. The fact that this is a large number is encouraging. And if you ask what is the reaction rate per deuterium, because since I like to compare with the freshman cones and everyone else, then you can get this kind of number. Now we can extract omega using Arata's reaction rate. And that goes like that. If I assume helium-3 is millionth smaller than helium-4 production, which may not be correct, but this is a good exercise. Then I can compare this known number with the previous formula to extract omega, which is happens to 10 to the minus 22. This is assuming that helium-3 production as a normal process, which is 6 order of magnitude less than helium-4 process. These numbers are not the final, because as more accurate number becomes available, we can adjust that. Now, if I take all data, and one thing interesting is that this number, Arata-Zhang number, is comparable to Frashman-Pond's original number. Okay, 10 to the minus 8, and of course, this plus minus factor of 5 is different, but it's important that that is very similar. Of course, Arata is observing few watts, and so was the freshman Pons. Now, if you take and just compare that with this gamma factor. This gamma factor is actually small, whereas this is order which is more reasonable. And if you take Steve Jones, I don't know whether Steve Jones is here or not, but he is still claiming that the first observation of neutron is, as far as he can see, correct. Later experiment, he made a mistake and says so, but the first one, he said correct. Now, if I take Jones to mean regular channel, neutron production channel, then there are, this compared to Frashman-Pond's rate, there are more than trillion difference. Then I get the omega of this level. So we need more consistent, accurate, reproducible number to determine its omega and see whether omega comes out to be consistent. How many minutes I have? 5 minutes? Okay, now I will run through some of the conclusions and speculations for the next 5 minutes. Well, this is we have a method to calculate the approximate wave function, and one important point is that our formula do not show gamma factor. It's the occupation probability, and that seems to be consistent with the original Dirac conjecture. Although it's not rigorous proof, there is consistent. Next point is that there are several predictions we can make. This is what I said before. Now, ground state probability is expected to increase as temperature decreases. This is completely opposite to gamma factor at low energy. And of course, this needs to be tested from some experiment. And those numbers need to be modified as more accurate, reliable, reproducible data becomes available. The Arata Zhang was showing 2 experiments in which he compared with the ordinary bulk metal. And I see it wasn't completely zero. There was slight excess heat sometimes. And so the bulk metal may be doing it, and people may have observed. And Frashman-Pond certainly will claim he observed, but at the lower level. My interpretation of that is that the use of powder fits into this picture, and it has more surface area so that deuterium can easily absorb. So these two cases not really mutually exclusive. That is, one is more efficient, and another one is less efficient process. Of course, you can try many other methods, and this may be what's happening here. if we believe our theory. Now, let me show you future applications. It's very hard to get the good data. Arata published several good papers, so I can take a number from them. But hopefully I can finish this calculation by next conference. If these gentlemen gives me a data, George, for example, will never give me data. Mike promised that he will write up something soon. So eventually, and Kasagi gave me some, but now he has new data. So this is my appeal to the experimenters. Give me reliable, reproducible data to me, so that we can do the good science. And eventually, if you consider fermions mixed with the bosons, we can develop the solution for the two species coherent quantum state. We are working on this, and this may be applicable to transmutation, but with a big question mark. And so I don't promise by next. I think that's my conclusion. Thank you.
Thank you very much. Now for discussion.
Wait a second. Before we get into the discussion, I just want to mention that we're going to have a group picture in the garden in front of the entrance at 11 o'clock after, when we go to coffee break. And Mitch Schwartz, unfortunately, could not come. So we're going to start the second part of the session at 11:30 instead of 11:15.
So we can have a long discussion.
Can I ask my question? You said that for large n data, commutator becomes 0. And then the entities.
Let's see, I didn't get you.
For large n, commutators become 0. Then they no longer behave like classical.
Right, if commutator is 0, it's like a Hartree factor.
They're classical particles.
Right.
Then there's no question about sign compensation.
No, but they're in the same state. There are, I mean, in other words, what you're saying is correct, but they will be in the same state, so that when they're in the same state, at a zero momentum state, it'll be all right.
No, what is saying?
I know. Well, that's true.
Let me
The author.
Hey, you're not me. Give the wrong answer. What it says is that the solution will look like independent particle. The interaction between them is minimal effect, so that J can still compensate.
No, but unless they obey those statistics, there's no host compensation. So that's very crucial.
Hold it in your mouth.
Unless there's we cannot read the host statistics.
No, but
and then we cannot have host compensation.
No, the commutator is just saying truth. That is, delta KK prime becomes small,
right,
compared to the commutator. So the rule is still there. It just suggests it's getting small. Well, we can discuss this.
Yeah.
Sorry about that. It would be an condensate though here.
This periodicity doesn't seem to play any role in your theory at all. So this could work with amorphous grains or any little volumes.
Right. Now, let me answer that. This is a very important point. We are restricting to very small size.
Small size.
Like a million particle and 10 nanometer, 40 nanometer.
Right.
If I make a big track, like entire bulk metal,
yes, then
the concept of coherent quantum state start breaking down for us. Rate becomes very, very small. That is, we have to have a multiple of those to get that kind of rate. And our boundary condition is expressed, harmonic is the boundary condition expressly imposed from the beginning. So there is no boundary condition problem with bulk metal or periodicity type thing doesn't come into us.
Again, can you tell me why these individual particles, the 40 nanometers that Ravi uses, is any different from the grains in a bulk piece of metal? My view is that both the individual grains are little individual traps, perhaps, and with a rather big barrier between them. At least my
quick answer to that is that the grain may be connected to each other, while the particulate just may be separate, just making slight contact. That is, I'm treating each particle as one trap, while in the grain case, they may be interconnected with each other, and I may have to regard those entire several grain or whatever connected one as one trap, which is much larger trap. And as I make a larger trap, rate goes down. And so that's consistent with efficiency and inefficiency between two experiments. But both of them are doing essentially same phenomena. I think the fresh compounds were seen real thin way back. Yeah.
In Peter Hagelstein's theory yesterday, the size of the domain affected the reaction channels. In other words, whether you would see neutrons or U-4 preferentially and so on. That doesn't seem to appear in yours.
No.
This is what needs to be done to get that in.
Maybe you can give me a pumping or Peter's approach is more complementary. His theory is looking maybe different aspect of the same problem. Sure. While I'm doing my own. Okay.
I'd just like to make a comment. I think it's great. I mean, I think what's happening is people are just discovering the many-body interaction, and it's really important, obviously. In terms of things like, well, this question about periodic order, well, a lot of these things are, in a cooperative state, you get a cooperative state. You can get cooperative interactions, and periodic order is an incidental thing at particular time scales and particular crystal sizes and so forth and so on. And it's almost like just looking at like Wannier states versus block states, and it's great.
That's your stuff.
I know, but I mean, no, it's not though. It's not though. If you write down, if you go back to your initial Hamiltonian and you recast it, you actually can recast it into a scattering problem the way that you initially started out. I mean, in other words, well, I'm giving my talk, but the point is that many-body interactions are the key, and it's great.
Okay, I agree with that part.
Yeah.
No question anymore? Okay, let's back to speaker again. Don't forget to the 11 o'clock to take a picture.
You're saying my network calibration is wrong. Next on quite right. Next session is 11:30.
So, paper's not even
Ну, кто знает, он же как мурял бы. Просто идиотская цена 900, надо сейчас ему сказать, чтобы не больше. Все смеются, я 3-4 услугу могу. Только 500 же стоит, таких цен нельзя вообще. Тоже смеются. Oh, c'est bon, pour nous c'est grand plaisir. Pour nous c'est grand plaisir. Ce soir c'est grand plaisir. Лысого, c'est проблем. Лысого. Все, значит, соберется здесь сегодня, а в Сочи уже железно будет ложаться контакт. Поэтому для них это... Привет. Сова. Merci.
The ionized particles, so the ionized particles will travel on and hit the target and create nuclear reactions. Then you observe the alpha, beta, gammas. Now I think it's a very, very interesting. With my small mind, I do not know how to explain that, so I'm asking for your help. Thank you.
You go talk to Cal. Francesco Scaramuzzi wants to say something.
Yes, about the picture, I did not buy the photographer here. He can bring the pictures for those who want to buy them this afternoon. So I would like to have an idea how many should he bring. Lift your hands, those who want to buy the picture.
How much is that?
$200.
$5 American. 10,000 lira. $5.
I can afford that.
It's 20 times.
There's more people downstairs.
Yeah. But you probably will find them when you come to dinner or tomorrow morning.
Okay, it's now 11:30, and Victoria Volante is our first speaker, and he has 30 minutes to see those, and then we'll have 5 minutes of questions. Can you say?
This job that has been done in framework of international cooperation between ENEA, University of Rome, National Institute of Nuclear Physics, and Stanford Research Institute. So we will talk about particle dynamics modeling, helium-4 decay, channels of reaction, tritium production, and estimate of excess of heat production. We start our model by assuming that there are electromagnetic field created in the lattice when deuterons in metal lattice like palladium or nickel are at high concentration, so the atomic fraction is close to 1. And when we have coherent oscillation of the Fermi level electrons, I mean plasma. This analysis is a three-dimensional study that is available for palladium and for nickel, because the geometry of the cell in the hydride of palladium and nickel are basically the same. And also the electron Fermi level is not too different. Basically, we want to investigate the effect of this electromagnetic signal on the dynamics of the particles, I mean of the deuterons in the lattice, and the effect of this field on the nuclear decay of the excited helium-4 formed by the interaction of the deuterons. We can assume that deuterium and hydrogen within a metal lattice like nickel or palladium can be considered to be ions, simply because the electronegativity of the metals is very high compared with the electronegativity of the ions, more indeed, because they can be considered into a ionic state, as studied in deep by Charles. Of course, this is a simplified scheme. I don't want to go in this very delicate matter. So we know that this oscillation produced by effect of the charge separation is intense electric field, and the effect is an acceleration of the ions. trajectory of the ions are studied by means of the equation of motion, assuming that the deuterons belong to two populations. One is at rest in the tidal site, and the other one is a population of diffusing particles that is able to go towards the tidal site, passing the proper activation barrier that is in the order of 0.232 electron volts. We can show that the calculation reveal that the distance between the ions can be reduced below 0.1 angstrom. We use a simulation code, Claire, that allows also a Monte Carlo calculation to estimate the number of the effective trajectory to have a collision that is in the order of 1 on 10 to the 5. So the code has been developed at Atenea and enhanced in the framework of a cooperation with the University of Illinois. Just some figures to clarify the concept. Normally, the deuterons are diffusing between octahedral sites, passing a barrier that is in the order of 0.2 electron volts, while if their energy is high enough to go inside the lattice when the thermodynamics of the system is suitable for that, they go towards the tidal side, and this barrier is higher than this one. So it's obviously that all this machinery works if we have a not equilibrium situation. So if the system is characterized by flux of deuterons, so the diffusion takes place. We can simplify this scheme by taking the projection of this cell in the ZX plane, and we see here 1, 2 atoms, atom number 5, and so on. And the oscillation of the electronic clouds creates an oscillating electric field towards the planes. For the sake of simplicity, we can assume that the oscillation develops along the z-axis, so we have these electronic clouds on the top of the cell and on the bottom oscillating and creating this electric signal inside the cell. Some previous calculation led this formulation for the equation of motion in dimensionless form, where the first term is obviously the second derivative of the dimensionless coordinate of the generic particles I, and the first term is the force created by the signal, while the second one is the repulsive force due to the ion's charge inside the lattice. Alpha is a factor taking into account the orientation of the oscillation. Q I is the charge of the particle, P is the electron charge, ρ n is the number of charge participating to the oscillation, m is the mass of the ion, omega is the frequency of the signal, L0 is the characteristic length of the system, the lattice parameter basically, that is the same for palladium and nickel when we are in hydride phase. Gamma is a numerical factor avoiding singularity, it's close to unit, and psi is a phase factor that takes into account the value of the signal, so when the particle enters the system. So the signal is with a shape like this one. This is a dipole signal. So the system works like a ionic trap, as Professor Kim said, has this morning, but it's a simplified system, so just one cell. The frequency can be estimated by using the classical expression for surface plasmon frequency, and we know from the literature that plasmons are spontaneously created at the interface between metals and electrolyte, or metals and gas under some condition. We see from our study that the distance between deuterons decreases if the initial conditions are suitable for that, decrease below 0.1 angstrom with a frequencies that is in the order of 1 for 10 to the 16 second to minus 1. There is a parameter that is critical in this study, and is the ratio between the amplitude of the field and the frequency. If this ratio is maintained in a proper value, we have some interesting effects in dynamics and in the nuclear decay process. If we reduce the frequency, so I mean I am increasing the ratio between the frequency of the signal and the amplitude, because the amplitude is maintained constant in this analysis, you can see that the distance decreases well below 0.1 angstrom. So this distance is large enough, is small enough to have some interaction. The energy of the particle is also a function of the frequency, as you can see here, and we can see that the particle that is able to enter the proper boundary condition in the lattice can gain an energy that is in the order of some TeV, and in reducing the frequency, I mean increasing the ratio, the energy increases too. If the boundary condition, the initial conditions are not good to have an interaction, the evolution of the particle trajectory is the following one. So no collision at all, because the system is highly nonlinear and it's strongly affected by the initial condition, of course. We can do this classical approximation because due to the frequency of the system, of the signal, we can simply verify that the particles gain many photons from the system. So the system is highly nonlinear, and we can make this classical approximation. Now, after this study of the motion of the particle, we can say something about the helium-4 decay. Of course, this is a simplification, but we start from the study done by Giuliano and Emilio on the effect of the plasmon on the de-excitation of helium-4 formed in a lattice, and we want to study what happened in terms of the parameters we have used for dynamics. So we want to study how the system answers when we change the amplitude, the frequency, and then the ratio. We estimate this coupling effect between the excited nucleus and the lattice electromagnetic field towards the coupling between the current in the nucleus and the potential vector of the field. But for the current in the nucleus, we assume the single particle approximation, considering that the proton is oscillating, producing this current. So we see that the energy released by the excited nucleus, as hypothesis, is supposed to be given to an infinite reservoir, that is a region having the dimension of the wavelength of the electromagnetic signal, where coherent behavior can be assumed. So coherence is at the basis of this analysis. We can also assume that this region is not dramatically affected or damaged by this nuclear decay because it is large enough and the answer has evolved. The excited alpha particle that goes to the ground state do this process by the intermediate effect of the Fermi electrons that participate to the plasmons that in some way interact with the lattice, and I want to spend some words in the conclusion on this. So according with the semi-classical approximation I have introduced now, and considering this coherence domain as an infinite reservoir, we can assume that the distribution of the electromagnetic field is not strongly modified by the nucleus decay, and then the completion of the matrix element is carried out just considering the wave function of the nucleus in the initial and final state. So we start from the proposed scheme by Giuliano of the decay process from the excited ground state. We consider the interaction potential as function of the charge of the particles, so in the proton oscillating in the nucleus, the momentum operator, potential vector, and mass of the proton. So I said at the beginning that we suppose that the oscillation takes place along the zeta direction. So in this case, the potential vector can be described by means of this relationship, where A0 is right the ratio between the amplitude of the electric signal and the frequency of the signal. For A0, we can assume a value, we can limit the value in a range that is not far from the value estimated on the basis of the classical plasma theory. So the wave function is can be calculated as overlapping of the three states I mentioned before, where omega 0, omega 1, omega 2 are the energy units of h of the respective energy level. And from the Schrödinger equation, with proper initial condition, with some mathematical ending, we find again what Giuliano found, that the controlling step is the 0-1 step, because C1 is 4 order of magnitude larger than C2. So the mathematical handling gives the so let me say the stimulated transition probability, and this function of this omega 0 value, and of the interaction time, and of the matrix element, of course. So that we, in this parametric study, see that maintaining constant the amplitude of the signal, we have probability of decay in the order of 10 to minus 3 for a frequency of 10 to the 15 7 to minus 1, while the probability decrease below 10 to minus 5 for a frequency of 10 to the 16. Now, we can take advantage of these results to make a raw estimate of the effect on the reaction channel in the lattice. So we have the well-known relationship that gives us the probability to have a channel for a compound state that is given by the ratio between the partial width of the channel on the sum of all the partial widths. For the deuterium reaction in vacuum, we know that the maximum partial width is given by this relationship, and the result is very close to the limit given by the uncertainty principle. So we can assume that in our system, this value is the partial width for the stimulated process that is very fast due to this electromagnetic coupling between the nucleus and the lattice field. Now we want to make a comparison of this value with the value of the reaction we are used to see in the vacuum, and to do that we can introduce a condition that is a ratio between the probability towards by means of the ratio of the decaying cross-section, let me say in this way. We can borrow this expression by Bate, 1986, for photo capture process, and we can apply the detailed bands to have evaluation of this cross-section for the reverse process, introducing in this relationship the matrix element we estimated above and the frequency of our process, and this is the nuclear volume. So the other terms that we have to compare with this can be obtained by literature data, I mean Bulgarian National Nuclear Data Bank, cross-section value for 1 keV, and this cross-section value is of course deprived by the gamma term, because we are accounting for decay problem, and the previous cross-section considered just this aspect. And this ratio is 10 to the minus 4, so that we have that the partial width for the deuterium-deuterium reaction with neutron or proton is 10 to the minus 4, this partial width of the stimulated transition. For the gamma decay, we can assume that basically is maintained with the same ratio that we have in the vacuum, so it's an unlike process. So that at the end, or we can assume an electric quadrupole decay, but the results at the end is that the probability of the stimulated transition is 1, is much larger than the other channel we know. These results are obviously indicative, but it is in accordance with the experimental results of excess of heat without the neutrons and gamma ray. Now, we want to stress this model, going towards some parametric analysis for the problem concerning with the tritium production that Michael showed me yesterday. And we know that this tritium is reality. There are also other estimated data, measurement of that by Giuliano Mendoli, Daniele Gozzi, and so on. So we can apply again this model, assuming here for space reason I avoided to report the well, but this is the shape of the potential. We assume that this potential is done by a square barrier coupled with the external Coulomb potential. So this is the nucleus, and the proton is oscillating inside, and we want to see if there is some condition that can promote the channeling even tritium in the framework of the proposed picture. So we can do that, estimating the probability of the proton position by means of the calculation of the wave function in space representation by solving the Schrödinger equation, where the potential has been built in this way. Here we have this Coulomb potential times the square barrier plus the perturbation that is this electromagnetic C. E is the eigenvalue. So we can have this representation for a system where this perturbation is switched off or switched on and can change the intensity. The interaction potential is calculated in the same way I showed before with this product, but we add a little information more, so we consider also the space dependence of the electric field around the nucleus simply by making a Maclaurin series of the expression that appear in the dynamics equation. The boundary condition is that the wave function is 0 for x large enough. So large enough means that it's at a distance that cannot be reached by a particle flying at light speed. So this is the proton localization probability. You see that it's far away from the nucleus, and the probability is in the order of 10 to the minus 5. This is a qualitative behavior. For the neutron, we can repeat the calculation. So the perturbation is switched off for this evaluation. So we adjust the square barrier here, and we see that the value is quite similar, so as it should be. But the shape is different because we don't have this repulsive effect of the Coulomb barrier. So that means probably the neutron is going out with reduced energy, as is, it's 2.4 MeV against 3 MeV of the proton. When we switch on the signal, we have that for the proton, for the neutron, the system remains same. For the proton, the situation changes, so we have that this probability increase of 2-3 orders of magnitude, even if the proton is localized more close to the nucleus, but significantly far away. And if we increase again this signal, I mean, if we decrease the frequency or increase the amplitude of the electric field, we have a strong effect of localization of the proton on the nucleus. And this value is strange, but it's the same value that gives a significant transition probability with electromagnetic coupling with the lattice field. So we can go on for the last topics. So here we have some estimate of the excess of heat production. So we can do is just an estimate in order to see how this picture concerning with a diffusive mechanism of promoting the reaction in the framework of electromagnetic field, we can use two approximations, or by considering the small size of the particle compared with the lattice cell size, we can assume the reactivity in vacuum, and we can give 24 anything for the reaction in accordance with the previous analysis. We can use the classical relationship when we have two particles staying in two different populations at two different energy levels, ND1 and ND2, where ND2 is the population staying at rest, I mean the target in the tetrahedral site, and ND1 is the population of the shock, so the particles that diffuse and enter the system and are accelerated by the electric field. So this fraction here, the fraction in tetrahedral site, can be assumed roughly close to a phase transition in the order of the density number of the deuteron staying in the lattice. The other population density number can be estimated on the basis of the analysis we have done. So first, we have to multiply the number of deuterons staying in the lattice for the Boltzmann distribution function, accounting for the energy required to go towards the tetrahedral side, times the probability to have a collision that we estimated on the basis of the Monte Carlo code that is solving continuously the equation of Modi. So, the other possibility is to apply the relationship proposed by Giuliano, including this effect of the effective collision and of the energy required to go towards the tetrahedral site, and accounting for a D-wave process towards the Gamow factor. Well, the calculated results show that if we consider energy in the order, this is the value of exchanged Coulomb potential energy calculated by the simulation code in the order of 1, 1.5 and 2 keV, we have that for the first approximation, and I call the vacuum approximation, we have that the density of power results to be ranging between 13 watts per cubic centimeter up to 1.5 keV per cubic centimeter, while by using the other approximation we range from 1 watt per cubic centimeter up to 12 kilowatts per cubic centimeter. And we have an effect of the temperature that increases the power density of a factor 5 over 50 degrees of temperature variation. From the experimental results, we know that this factor 5 can be justified by increasing of the temperature of 80 centigrade. But in this simple model, we neglected the loading due to the increasing of the temperature. So we have to accept this compromise for the moment. The main objective is to study the effect of the temperature towards the application of this Boltzmann distribution. So I can make a consideration at this point. If we increase the temperature, probably the concentration of the deuterons in the lattice decreases, but increases the fraction of deuterons going towards the tetrahedral side because of the Boltzmann function. So they can maintain the reactivity significant. So let me make conclusion. So there is a possible mechanism producing collision between deuterons in the lattice. We can have, in the framework of this field produced by plasmon, a shift of the decay channel of the excited helium-4 nucleus. And we can say that the fraction of the X-ray produced of the charged particles can be ascribed to these accelerated ions inside the lattice. So this mechanism is a consequence of the interaction of the field due to the plasmon with the ions and the nucleus. This ratio is playing an important role, and I use 10 to the 15, 10 to the 16, 7 to -1, but I had private communication from Professor Stramenos that this frequency is going towards 10 to the 14. This is encouraging us because it increases this effect and does tell us that no strong electric field are required. Because I estimated the frequency of the signal in terms of classical plasmon theory, but we have effect due mainly to the electron mass, effective mass in the lattice, and effect due to the roughness of the surface that shift the wave vector of the electromagnetic wave traveling on the surface, and we can have also other effects who are to like an harmonic effect that can shift strongly this frequency, but it's a particular topic. So loading ratio and temperature plus this ratio affect the excess of power production. That we can say that the field varying amplitude can seem to have a rule for the tritium production. Before finish, I want to mention that all the co-authors like to remember Giuliano, and this lecture has been given in memory of him. Thank you.
Questions? Yeah. Douglas, yeah.
Thank you. Two questions. I would have thought that some damping comes in. I don't see any damping terms in your work.
Well, I estimated you are right, it's a good question. I have done some calculation including the damping due to the, I mean from the particle, due to the shape of the potential inside the lattice cell. But we have seen that this effect in the framework of this simplified picture seems to be negligible, and in any case is playing in favor of the collision of the particle. So that's why I neglected in this short exposition of the. But there is a paper published on fusion technology accounting for these terms too.
Okay, and the second question is, how would you say that variation is cross-section of incoming energy? I mean, we heard data which shows rough agreement with the potential well effect, plus a screening effect of 600 electron volts. How would you predict the variation of energy then?
Well, I haven't done this. This is I saw just a quantitative analysis. Thanks. I check your thanks.
Are there other questions? I have a question.
Yes.
With regard to the occupation of the tetrahedral site, you know, I know that things are really well characterized at low temperature, and of course there it's just octahedral. Is there some kind of experimental indication that the tetrahedral site would ever become occupied?
Well, there is just an estimate by Coriani that in terms of thermodynamic analysis, they say that due to the expression of the chemical potential of the deuteron inside the lattice, the chemical potential should become infinite for the entropy when the concentration becomes close to units. The only way to avoid this unacceptable thermodynamic condition is that the system rearrange occupying the other sides that are tetrahedral side, and this produces an increasing of the free energy, but is limiting the chemical potential too.
That's a question. I mean, that's a question of temperature, of course. I mean, when you're down I mean, it's known from the spectroscopy that it occupies the octahedral sites when you're down near 10 degrees Kelvin. You know, so all right. Well, that was. All right. Well, let's we'll move on now. Right. The next talk. The next talk is by Tadahiko Matsuno, an old friend, and well, he'll tell you the talk. Here's your mic. Thank you.
Buongiorno, buongiorno, signora, signorina. Mi chiamo Tadahiko Mizuno. So I'm going to present you my title, Conformation, Heat and Product Induced by Plasma Electrolysis in the Liquid. I'm going to show you my extraordinary heat generation during plasma electrolysis. This is a case of extraordinary heat generation during plasma electrolysis. This is each stage of plasma electrolysis. It's a little bit difficult. You can see this is the first stage, and second stage, and third stage. And this is no excess heat. The plasma is like that. And after that, this plasma state shows 10% excess heat, okay? And the third, this is 30% excess heat generation. The plasma state completely like that. It's completely different, you know. And many people wanted excess heat, but it's very difficult to reproduce such kind of things, okay? And I will show you again.
Material and experimental condition, please.
Pardon?
Material and experimental condition, please.
Okay, I'm going to show you. And in the beginning, I want to show you very large data. Okay? This is large excess heat generation. You see, it is the excess heat is up to 200%. Okay? I want to show you in the beginning. So it's a very important result. Oh, anyway, I'll go back this transparent parenthesis. Okay. Here, this shows the content of my presentation. In the first, I will explain the experimental procedures, material electrolyte heat calibration method, and element analysis method. Second, I will show you the excess heat generation during the plasma electrolysis. When we obtain much excess heat, we always find anomalous element in the electrolyte and on the electrode surface. Finally, I will present you a theoretical mechanism that explains these products, including the excess heat. So I want to share my time to host Dr. Takahashi. It is a very nice mechanism. He is very considering some kind of hot friction. Okay. I used high purity of tungsten, 99.95% pure. That dimension was 5 times 10 times 0.3 millimeter thickness. Electrode water was distilled water. I use the light water purified through a mini-cube filter up to 18.3 ohm per centimeter of resistivity. This is a tungsten sample of the rectangular shape and big rod. Zero dimension cathode and anode are as shown in these figures. This shows a brief drawing of the heat measurement arrangement. We measured heat by a method that is a combined system with open cell and flow calorimeter method. This method can estimate heat generation in real time. It's a very important point. And this cell is surrounded by the another bigger glass cell. Inner reactor vessel and outer primary coolant envelope. There is primary cooling water between these two cells. I installed a heat exchanger pipe in outer envelope, and secondary water coolant was passed through the tube. Okay. The secondary water is circulated by a pump from a constant temperature bus. The top of the cell is plugged with a Teflon rubber cap. But it is not closed because several holes are opened, and in the cap to allow decomposed hydrogen and oxygen gas to escape. This effluent gas carries away a portion of the heat, so the heat generated in the cell is underestimated. The electrolyte temperature in the cell is measured with a Teflon-covered thermocouples. The magnetic mixer at the bottom of the cell ensures the uniform temperature distribution. The temperature of this secondary coolant is measured at the inlet and outlet of the heat exchanger tube by thermocouples. Finally, a thick styrofoam insulation surrounds the outer chamber of the cell. This is a photograph of main part of measuring system. You can see the cell, heat exchanger, anode, cathode, magnetic mixture, and thermocouples. This is the cathode, anode, and heat exchanger, and thermocouples, and magnetic mixture is here. This figure presents several factors for the heat out during experiment. Here, heat out can be considered as a vapor, heat by coolant, water decomposition energy, heat release, and electrolyte heat. All of the heat out factor must equal the inner power during calibration. The input and output heat are obtained with these formulas. Here, we did not consider the vapor contribution. All data, including voltage, current, temperature, and mass of secondary cooling water, are collected with a data logger every 10 seconds. Data from the logger is captured by the computer and finally recorded on diskette. The error of the input power watt and output heat can be estimated from the stability of power supply, temperature pressure, and flow rate fluctuation. This error is estimated as 0.84 watt. We calibrated the heat recovery with an electric heater. We take the anode and cathode assembly out and install a dual heater in the same position in electrolyte. And this is the input and output power relationship. Heater current, and voltage, and this is the electrolyte temperature. Electrolyte temperature started around 30 degrees and increased and up to 100 degrees, it means boiling point. And then we increase input power. And the lower graph, you can see the input power is green dotted line, and the red line is output power. And you can see the ratio of out and input is almost 0.89. But you can see this point, it is meaning that this recovery is decreased because the temperature go up to boiling point. So the meaning we did not consider the vapor contribution. So heat recovery decreased. The power profile was the same as the electrolysis. Lot of power at first, decreased later. You can see the out-input ratio stayed around 0.89 during the measurement. In other words, the flow calorimeter recovery rate is 89%. According to the result, I can say a steep input change did not affect on the heat recovery. This heat measurement system can precisely follow input and output heat. The only difficulty is the method is uncertain at the low input power range because the temperature measurement error was 0.1 degrees centigrade. However, the precision of measurement is enough because input is usually above 70 watts. We have done all of the measurement in the electrolyte. That concentration was 0.2 mole of potassium carbonate. And I used voltage 60 to 220 volt. Current density usually 0.3 to 10 amperes per centimeter. So I keep the temperature, electrolyte temperature, 60 to 100 degrees centigrade. I show you a typical correlation between voltage and current density at 80 degrees centigrade. Normally, cathodic electrolysis occurs under 40 volt at 80 degrees. However, above 40 volt, plasma electrolysis occurs. During plasma electrolysis, current-volt relation is inverse to normal electrolysis. As voltage increases, current decreases. Material in the solution and deposition at the bottom of the cell were calibrated by ICP analysis. The element on the electrode surface was analyzed by the EDX. The element was then melted by an acid and calibrated by ICP method. This shows an example of measurement result for an ordinary hydrogen production. In this case, a tungsten plate was electrolyzed at 40 volts. When electrolysis began, the temperature reached around 95 degrees. Current reached at first at 5 amperes, or 200 watt input. As the temperature rose, as the current density current decreased to 1.5 ampere, it means 75 watt. But in this case, we did not observe excess heat production. The output heat can clearly follow the input power. In this figure, you can see at 80 volts, the entire cathode is covered with the plasma. In the first, the current reached 5 amperes because the plasma discharge had not yet begun. So input normal at 400 watt. Simultaneously, the start of light emission, the current level decreased, falling to 1 ampere after 300 seconds. It was about 80 watt of input. The lower figure shows the appearance of excess heat generation here. This is 100%. This is excess heat generation. This is a case of high purity tungsten result. After the cathodic electrolysis, high voltage plasma electrolysis started, and after several hundred seconds, you can see a clear excess heat generation up to 200% here. And this case is almost same as before, but rather weak excess heat generation. In the experiment, I wanted to see the plasma state during excess heat generation. However, I saw excess heat generation very small. The maximum ratio is only 130%. Anyway, I have an excess heat here, 30%. And I'll go back photograph. Again. Here, you can see the difference of plasma for excess heat generation and no excess heat. Apparently, the plasma during excess heat generation at this point, the light is very strong and it seems like a fireball around the electrode. Especially, discharge paper was glow up at the center of the sample. You can see this is time 60, only 125, this 500 seconds, very short time. So it's a very strong plasma like that.
I'm sorry.
And this shows another case of tungsten where the thickness was 0.3 millimeter. The output and the input ratio are changing with time. You can see this is input volt. I kept 200 volt and decreased 100 volt and finally 60 volt. The current in the beginning was like that, 5 ampere, and decreased around almost under the 1 ampere and like 0.5 amperes. The temperature go up and stay around 80 volt, 80 degrees centigrade. And this green dot line is the input power, and this red line is output. This means you can see that this is a net excess heat like that. This is out and the input ratio. So it means that excess heat reaches more than 200%. The net power is 100 watt. It's quite a large excess heat. And you see, this excess heat almost continued more than 500 seconds. And this graph shows sorry. We always observe some deposition bottom of the cell in the case of excess heat have generated. You can see exact excess heat, this is a typical same image of the deposition. You see, it's a very big particle. The total volume is 50 milligrams. Many elements were confirmed in the electrolyte deposition and the electrode surface. On the other hand, there were fewer elements for the case of no excess heat evolved measurement. A typical measurement result by the EX is shown in this figure. There were several elements were detected, such as calcium, titanium, chromium, and iron, and zinc. Especially, they were observed at the center of the sample. Meanwhile, other elements were detected in the solution. These were derived from the element on the electrode surface and the deposition bottom of the cell. Typical analyzed element distribution are shown in this graph. Here, the difference between the case of excess heat generated and no excess heat are clearly shown in this figure. Especially, you can see a strong iron, chromium, titanium, germanium, and indium. Here, I have to say summary. Excess heat was confirmed during the primary electrolysis of tungsten electrode. Many elements were detected on the electrode and in the electrolyte for the case of excess heat generated experiment. Experimental results can be well explained by the photofission mechanism. This photofission mechanism was already shown in the poster session by Dr. Takahashi 2 days before. Thank you.
Quite a few questions that people have. Yeah. Why don't we start with John Paul?
Can you tell us something about the anode, what the material of the anode is, and what the geometry of the anode with respect to the cathode?
You mean anode arrangement?
Anode, how did you position the anode? What kind of anode?
Very close cathode, like cathode is like that, and anode is like that, and very close. It's very important point. Yes.
It's platinum?
Yes, platinum wires.
Platinum wires.
Usually we need a very big difference, but the area, very small cathode and large anode.
Have you studied neutrons and gamma rays as earlier? Is it in your earlier experiments?
Yes, I can do that. But in this case, I use the light water. In this case, I have never observed gamma and neutrons, nothing. But however, I don't know. However, if I use the heavy water and platinum electrode, for example, potassium carbonate, I sometimes observe very weak sporadic neutron radiation, not so much.
How much higher frequency measured change volts or current you power matter?
You mean I use this constant current, constant volt I keep the constant volt, but the current is very changing, so it's very difficult to measure it.
Are there any other questions? I was wondering how you, did you analyze both the cathode and the anode afterwards?
Yes.
And did you find anything on the anode?
No.
Just on the cathode?
Just like I measured the cathode surface. So, and especially the bottom of the cell, and a lot of materials.
Wait, what were the materials?
Especially, I can say, almost all material is 70% is iron.
Iron? Iron?
Yes. And another is zinc. And I measured the ICP method in Germany.
What kind of levels were they? I mean, what parts per million or per billion? I mean, how did you determine how much these levels increase?
Use the microphone.
I'm sorry. I'm sorry. Yeah, I can use this one. I'm sorry. Did you determine how much these levels had increased?
Yes. So you mean the impurity you have?
Yeah. I mean, yes. And,
yes.
And how much were they?
Okay. Maybe you can see this way to me. You see? This is before impurity level like that. And the excessive, if they are excessive, okay? Very big difference.
I see. Okay. There's no iron in before at all.
No, not at all.
Wow.
It's under the station.
Okay. Oh, yes. Yes.
Similar question.
Oh, I'm sorry.
You mentioned this can be accounted for by the photofitting process. Can the heat be accounted for in terms of the reaction products?
Some kind of photofission. You are concerning the photofission mechanism.
Your last summary slide said that this could be explained by the photofission process.
Yes, it's a little bit difficult. So I want to ask Dr. Takahashi. Maybe he has hot fission gas because it's very important.
But my question is an energy balance.
Yeah.
If you measure the products, can you
I
account
see.
for the
I
energy
understand.
production?
Yeah. I can say the order is almost same. However, the exact value is not completely coincidence with the energy balance.
Another question is, did you measure isotope ratios?
No, not. I'm not measure the isotope ratio because it's very difficult, very small particle in the bottom. But anyway, I can measure very exactly.
Yeah, I find your work fascinating, and I've made my own copy of your cell. What other electrolytes have you used? Only potassium carbonate?
Yes, potassium and potassium sodium, and maybe two of them.
Yeah. Have you tried lithium compounds?
Yes, I tried, but I concentrated my effort this potassium carbonate.
Why have you chosen potassium particularly?
Because I tried two of them. The excessive is very easily observed in this case.
With potassium carbonate?
Exactly.
I see. Another problem, of course, with these cells is that the cathode erodes away very, very quickly. What sort of a lifetime are you getting?
Yeah, exactly. It's very easy to decrease the area. Maybe we can keep maybe with 3,000 seconds or less. That's a problem.
Yeah, I see. I've tried using a spark plug. I found that works very well indeed. If you remove the earth electrode and use the central electrode of an ordinary automobile spark plug, a long reach spark plug, that lasts and lasts and lasts. I've spoken to the spark plug manufacturer. They won't tell me what they make it of. It's a commercial secret, but it does last. And of course, the other way is to take away the electrode altogether, and to produce an electrodeless plasma between two large areas of electrolyte joined by a small channel.
Yes.
and then you've got no electrode problems at all, because the electrodes then are electrolyte and they're self-renewing, and it goes on forever.
Wow.
I get best results with lithium hydroxide.
Okay. Are there other questions? Yeah, Gene.
Real brief, have you any plans to go to high pressure? And would you speculate as to what would happen at high pressure?
Yes, it's a very important point. If I want the excess energy more, we have to the temperature go up, and more the high voltage, maybe, I don't know exactly. But anyway, I tried only to 200 volt, and the temperature is 100 degrees centigrade. So if I increase the temperature more than up to 100 degrees, you can obtain more excess heat, maybe.
But pressure?
Pressure is very important. My system is completely open cell. So if I have to use a closed cell, maybe I can get more excess heat. Very important point.
Okay.
Do you have plans to do that?
Yes, exactly.
It's time to move on to the next speaker, who is Are you A. Rosetsky? A. Rosetsky? Oh, well then, that's unfortunate.
Use the microphone, Scott. Oh,
is A. Rosetsky?
Yes.
Oh, I'm sorry. Good, I'm glad you're here. I'm the chairman, I should be using the microphone, I apologize. All right. Okay, this is 25 minutes, but it's the last talk.
Dear colleagues, ladies and gentlemen, I'm Francesco Alexei from Moscow Physical Institute, Russian Academy of Sciences. I would like to present you the results of application of CR39 plastic track detector for detection of DD and DT reaction products in cold fusion experiments. The problems of identification of different particles and background-foreground separation are very important in cold fusion experiments. CR39 plastic track detector, which is used for registration of heavy charged particles, is a very convenient instrument for detection not only DD fusion reaction products, but also DT ones. This detector has characteristic response to every type of particle from DD and DT reactions. Charged particles are registered directly as neutrons through the secondary recoil particles or nuclear reactions. Particle tracks on detector became visible after each and are investigated by microscope technique. The goal of the book is studying of CR39 detector response to different types of particles from DD and DT reactions in different conditions of experiment. Outline of the presentation is follows. At first, I will talk about CR39 track detector and its properties. Then I will present the results of calibration this detector by DD and DT reaction products. And then I will talk about the measurement of DT reaction yield in palladium oxide gadget structures and the reaction yield in the experiment with low discharge of deuterium. Last, I will present the results of measurement of DT reaction yield in palladium oxide structures. CR39 plastic track detector represents polymer with this formula with density 1.3 gram per cubic centimeter. In this work, we used CR39 detector produced by Fukui Chemical Industry Corporation in Japan in 1996. After exposition, the detector was issued in 6 normal sodium hydroxide solution at 70 degrees centigrade during 7 hours. After the etching, particle tracks became visible and can be investigated by a microscope. The basic characteristics of track detectors are the etch rate ratio V, which is function of ionization and zero loss, and the critical angle theta c, the minimum angle when of direction of particle when it can produce track. It is easy to show that the detection efficiency for given type of particle is determined by the equation eta is equal 1 minus sinus theta c. If the value of bulk etch rate and track etch rate are constant, and for normal direction of particle, we can use a simple model of track pitch formation. In this case, the track diameter d can be expressed from the ratio v by simple equation. And thus we can estimate the ionization loss of the coming particle, and to determine the type of particle and to estimate its energy.